Hello and welcome back. In section 2.1, we get to work with an introduction to solving one variable equations. So we've already talked in chapter 1 about what it is to be an expression. Well, an equation is just a statement that two expressions have the same value. So some examples of one variable equations. X minus 8 is equal to 1. X squared minus 7x plus 19 is equal to 47. Square root of x minus 6 is equal to 11. 5 over x minus 3 is equal to x plus 2. These are all equations in one variable. You might have noticed that some of them have x listed in more than one spot. That's okay. As long as it doesn't have an x and a y, it is still considered a one variable equation. That one variable can be raised to various powers. It can appear under radicals, under denominators, things like that. That's okay. That would still be an equation. A solution to a one variable equation is a number that makes a true statement when substituted into the equation. EQN is a common abbreviation for equation. Now, problems can have multiple solutions. It can be more than one valid solution. Now, one other thing that's going to be a big topic in this this course is the idea of the domain. So the domain for a problem is the set of values used for a given problem. Typically, we would either have a domain of this is sort of like our universal set. From our chapter 1 work. So our typical domains, we might have the set of natural numbers. We might do the set of integers. And later on, we'll do the set of real numbers. So those are some typical domains that will be used. The solution set to any particular equation or problem is the intersection of possible solutions and the domain. So in chapter 2 and 3, our domain is going to be I, the set of integers, unless otherwise stated. We're then going to go back later on and rework some of the same types of problems, but expand our domain and see what the problems would have looked like had we been allowed to work with all of the real numbers. So it's sort of a spiraling type of curriculum where we hit the same idea multiple times in different ways. It really helps work with your long-term memory at that point. If you've seen the same topics multiple different ways, it moves your understanding from the short term to sort of the deeper, longer term understanding. Now, restricting to the integers is going to create what's called a closure issue. So that's the next big topic we need to look at. So a set is closed under an operation if applying the operation to any pair of elements of the set produces another element of the set. So we'll start with this set of natural numbers. We'll start with addition. Natural numbers n is closed under addition. You pick any two natural numbers, let's say 8 and 12, we get a 20. 8 is a natural number, 12 is a natural number, its result is also a natural number. While this is not proof that this is closed, this is just sort of an example to help show that it is closed. Proving that something is not closed is possible with just one example. Proving that something does work is not possible with only one example. But the natural numbers are closed under addition. Any two natural numbers you pick, add them up, your answer is also a natural number. However, subtraction, we don't have that anymore. So for example, I could take 5 and subtract, let's say, 16. 5 is a natural number, 16 is a natural number, but the result, negative 11, is not a natural number. So 5 and 16 are elements of n. Negative 11 is not an element of n. So that showed that in is not closed under subtraction. So in some of our problems, if we are working with a natural number domain, if there's subtraction in the problem, there's going to be the possibility that our answer will kick us out of that domain. Multiplication. Natural numbers, remember, are all positives. Positive times a positive will stay positive, so we don't have any sign number issues to worry about. And natural number times natural number, I'm not going to get any fraction or decimal results other than ones if I wanted to put something over a 1 or put a 0.0 afterwards, but we won't get kicked out of the natural numbers. So n is closed under multiplication. Seven by 9, 63. 7 is a natural number, 9 is a natural number, 63 is also a natural number. Again, while this isn't proof, it is an example showing that. Division, I'm going to give you the hint that n is not closed under division. And I'm going to ask you to pause the video and show me why. Okay, welcome back. So your example and my example might not be exactly the same, but we could take, I don't know, let's say 8 divided by 17. That is just the proper fraction, 8/17. So 8 is a natural number. 17 similarly is also a natural number, but 8/17 is not an element of n set of natural numbers. So we've proven that n is not closed under division, the statement that I made before I had you pause it. N is not closed under division. So if our equation later on has division in it, there is a possibility that that operation will end up kicking us out of the set of natural numbers. Now, I did mention before that typically in chapters 2 and 3 we're going to be working with the set of integers as well, so I want to look at those as well as far as closure. So we'll start with addition. If I take maybe -8 plus 5, I get a -3. -8 is an integer, 5 is an integer, -3 also an integer. I is closed under addition. And thanks to the integers also allowing us to have negative values, I is also closed under subtraction. -3 minus a -10 is worth +7. Each one of these are in the set of integers. Multiplication, still closed. -13 times +3 is -39. In the integers, in the integers, in the integers. No problem there. Division, though, we still have that closure issue. So again, I'll ask you to pause it and see if you can prove that to me. Okay, welcome back. Let's try -6 divided by, let's say 11. The result, -6/11. -6 is in I, 11 is in I, but the end result, -6/11, is not an element of I, the set of integers. Again, it's unlikely that you just randomly came up with the same two values that I came up with, but all it takes, again, is one example. Now, you might have noticed that it is possible to come up with an example that does stay within the integers. That's okay, as long as you can come up with one example that doesn't work. Even if you can come up with 100 other examples that do work, if you find that one that doesn't, we're no longer closed under that operation. So that's why these are more examples. They're not actual proofs, whereas this is a proof that we don't have closure. Proving that we do have closure is a little bit more work than what you have the background at the moment for. You would have to have a few more courses under your belt to go into that. So for now, we'll just do a couple brief examples demonstrating that it should work this way and not actually going through the rigorous proof process. And then the last thing we're going to go over in 2.1 would be then the types of equations that we're going to run across in this book. Well, really anywhere that exists anywhere. So one type is called the conditional equation. In a conditional equation, the solution set is a proper subset of the domain. We're going to also assume we mean non-empty proper subset. So an example of that x plus 8 is equal to 11. We can see that this should be 3. So our domain, let's make it I for this one. So our possible solutions for this thing, all of the integers, we go through the work and we come up with x equals 3. 3 is a proper subset of the integers. So we'd show the reader of that by putting that into some braces. So this is a conditional equation. It works for some integers. It does not work for other integers. For example, 0 would not work. 0 plus 8 will not give you an 11, but 3 plus 8 will give you an 11. So 11 equals 11. That would be how we would show that, yes, that does indeed work. We also have the possibility of an identity. So an identity equation works for all of the elements of the domain. So for example, 3 times 2x is worth 6x. If we just use the associative property, we get 6x equals 6x. So this is going to be true no matter what value x takes on. So for this one, even if our domain was just, say, n, this is true for all integers. And we can show that just dividing both sides by x. 6 equals 6. That's always going to be true. So this is an identity equation. It's always true for all the elements of your domain. That's as opposed to the other possibility we have is something that is never true for anything in our domain. That would be a contradiction. Basically something that is always false. X plus 3 equals x plus 4. If we subtract x on both sides, 0 plus 3 equals 0 plus 4, 3 equals 4. 3 and 4 are never going to be the same number. So if the variables drop out but we get a false statement, we have a contradiction then. So no matter what my domain was, even if I expanded it all the way to all of the real numbers for the domain, we would still not get any values that would ever work for that. Our other possibility would be no solution in the stated domain. So for this one, our domain will be a set of natural numbers. And let's say our problem is x plus 1 is equal to -9. You can see that we should be able to go through our work and get to x equals -10 here. But -10 is not in our domain. If you think back to our drawings of the real number system, here's our real number box split between the irrationals and the rationals. And within the rationals, the integers. Within the integers, the whole numbers. Within the whole numbers, the natural numbers. Here's where we were working, just in this little red area here. And here's where our solution landed us. So this one, we would end up throwing up just an empty set since we wouldn't be able to keep anything. Same thing here. We would just have an empty set. We wouldn't be able to keep anything. But just two different reasons we could come across the empty set. Contradiction will never work no matter what the domain is. No solution in stated domain would work if we changed our domain over from, let's say, the naturals to the integers, or the integers to the real numbers. There's something that would work, but not something that we can use on that problem based on the restriction placed in our domain. So those are the key ideas in 2.1. I would recommend trying out the exercises in 2.1. Just as a heads up, remember that to find the exercises, go to the back of the chapter, not just the back of that individual section. If you have questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.